Hi, Year 11s. So we covered these three questions in class, and there were quite a few people missing on excursions. So I decided to go back over it, but record myself. Also, I did a lot of these things on the board, and there wasn't heaps of space on the board, so it did become a bit of a mess um, with regards to all the working out and stuff like that. So I am going to do this in one take, pretty rushed. So if it isn't as polished as it could be, that's it. But hopefully, for those of you who weren't there, this will give you a chance to not end up a little bit behind. For those of you who were there and are feeling like a bit overwhelmed because we did cover a lot of stuff, we pretty much did calculations for a full 100 minutes. You have a chance to go back over it at your own pace, replay bits that you need to, and so on. So hopefully you end up understanding all of this and could potentially do it if a question pops up. Okay, now we're looking at hydrocarbons or any sort of molecules like that that we can combust or burn. When we do that, we can get energy out of those, and we have been exposed to a couple of equations that help us quantify the energy that's released when combustion reactions occur. So I'll chuck them at the top here. So we have Q equals M times C times delta T. Now, just a reminder that M is our mass of our substance. Now, it'll be the mass of a substance that is absorbing or releasing Q, which is our heat energy. C is our heat capacity of whatever substance we are talking about still. So each substance will have a heat capacity which tells us how much heat or how much energy it takes to change its temperature for a certain amount of it. And the last bit, which is probably the most simple, the delta T is the change in temperature. Now there is another equation which is Q equals N times delta H. Now, N should be pretty easy to remember. That's our number of moles. And delta H is a term called enthalpy change. So delta obviously means change, like usual. I'll just redo that and make it fit in here. So enthalpy change, it pretty much is talking about like a sort of internal energy within the bonds of our molecules. So when the substances react, you have reactants and products, and if we compare the amount of bond energy that's in the products or reactants and the products, there will be a difference. Essentially, there'll always be a difference, and the difference is our enthalpy change. Now, if there is a difference between the reactant and products, then that difference will have been released often as heat. Okay, so if we look at this first question, it tells us that a beaker of water was filled with 150 milliliters of water. A Bunsen burner was placed under the beaker and allowed to heat the water until it reached 44 degrees degrees Celsius from 20 degrees Celsius. So what I'm going to first do is I'm going to use this highlighter and highlight the parts of this these couple of sentences that are most important to us. So first of all, this here tells us how much of a particular substance, in this case it's water, that's the stuff that's going to be absorbing or releasing heat. In this particular case, use a Bunsen burner to do the heating, and the temperature change we have we can calculate from these two values here. So we know what the final temperature is, so we know what the initial temperature was, and so we can calculate a delta T. Now, so we'll just formalize that here. How much heat did the water absorb? This is Q. We're looking for Q for the water. So what we can do here is I can just chuck, let's put it here, Q of, and what we can also do, which I've mentioned a few times over the course of the term, is when you have a variable such as Q here, you can put a subscript under it just to make it really clear what like which substance we're looking at. So in this case, it's talking about the Q of the water, so the amount of heat that's absorbed or released by water. And that will be equal to the mass of water times by C, the heat capacity of water, times by the delta T, the change in temperature of the water. Now I'll just go over here and start quantifying those values. So the mass of water, while we're not explicitly given the mass of water, we do use the fact that we understand, the fact that we know that every milliliter of water weighs close enough to 1 gram that it doesn't really matter. So that means our mass of water is actually 150 grams. 150 mils is 150 grams. Now our heat capacity of water is going to be 4.184 joules per gram per degree Celsius. Now again, this value is, this quantity is telling us that it takes 4.184 joules of energy to raise a gram of water by 1 degree Celsius. So every substance will have a different value. That's why for water we use this value here. If we were heating up a block of metal, depending on what type of metal it is, it would have its own heat capacity as well. And our delta T of water is going to be our T final minus our T initial. So what it ends up as minus what it started as, which will be 44 minus 20 degrees Celsius, will be 24 degrees Celsius. That's our change. So all we have to do is we just chuck that into this equation. So we have 150 grams times by our 4.184 joules per gram per degree Celsius times by our 24 degrees Celsius. And bear with me, I'll just chuck this into a calculator. I cannot do this myself. 150 times 4.184 times 24 is equal to 15062.4. Now the units, you can hopefully remember that the units of energy is joules, but just to be sure, let's just cross some of them out to make sure. So we have grams here for mass, we have per gram here, so those will cancel out. We have per degree Celsius and degree Celsius, those will cancel out, leaving behind joules. Now, when you are working with these quantities on the right here, you need to make sure all the units are complementary. So if we've got our heat capacity of water in per gram, joules per gram here, that means that our mass, whenever we use it, is going to be in grams. Now there is, and if we do our Q equation, the result will be in joules. If we use this equation, I'll use this version of heat capacity. Now there is one exception, and that is this bit here. Now when we're talking about temperature changes, degrees Celsius is equivalent to the change in temperature in Kelvin. Now the individual values themselves, so for example, this 44 and this 20 would be different numbers in Kelvin, but the difference between them would still be 24. So if it's a change in temperature, joules per gram per Kelvin is the same as joules per gram per degree Celsius. Just be aware of that. If we're talking about just temperature, so if an equation ever just has temperature by itself, then you need to be clear which temperature you're using. Okay, now before we finish this one here, or before we move on to the next part of this question, we have a number with a large number of significant figures. What we need to do is we actually need to look back through our values that we used and figure out which value has the fewest number of significant figures, and we're going to use that to round our answer. So our water has 150 grams, that's 3 significant figures. Or it could be 2, but we'll just assume it's 3. Our heat capacity has 4, so 4.184, that's 4. But our delta T, our change in temperature, has 2, only 2. So 24 is 2 significant figures. That means our final answer will be in 2 significant figures, and that could look like this. 15,000 joules. The tricky bit is that while we know right now that we've rounded it to 15,000 joules, 15,000 joules is a perfectly legitimate number. You could do a calculation with heaps of significant figures, as in with 5 significant figures, and end up with exactly 15,000. So when we do it like this, it is a bit ambiguous. This could have 2 significant figures. You could also have 3 or 4 or 5. So to make it a little bit clearer, we can adjust this to 15 kilojoules. So we've divided it by 1,000 to show that it's actually 15 kilojoules, which is 15,000. But the fact that we have just 1 and 5 gives us 2 significant figures. We could also do something like this, which is 1.5 times 10 to the power of 4 joules. So we've moved the decimal point 4 spots to the left, 1.5, and now we are left with unambiguously 2 significant figures in our answer. Now we've done this a little bit, and the final question is, how much heat did the flame release? We know how much heat the water absorbed. This how much heat did the flame release, without giving any extra information, we are going to assume that the Q of the water, the amount of heat absorbed by the water, is going to be equal to the negative of the negative of the Q of the flame. So if the flame is releasing heat, the water absorbs it. Again, I'm making some assumptions here, which we'll talk about in the last question. Regardless, this is simply what you're gonna use. So that means our Q of our flame. So if we just readjust this, our Q of a flame will be equal to negative 1.5 times 10 to the 4 joules. You could, so it is very important. So if you're given the answer, of Q flame, just Q flame equals something, it needs to have the correct sign. This sign, this negative sign, is telling us that that energy has been released by the flame. Alternatively, you could say the flame released 1.5 times 10 to the 4 joules. You don't need the negative sign in front of the number this time because you are explicitly stating that the energy is released, so it is very clear. So both these answers here are correct, just giving the Q value of negative, showing that it's been released, or just stating that that amount of energy has been released as well. They both work. Cool, so hopefully that's nice and clear. So we're going to go over to question 2, which is also relatively simple, maybe just a touch harder. So question 2, we have an alcohol spirit burner. So what that is, it's imagine like a little glass bulb. It's got a little opening at the top, and we end up with a little like a wick that's dipping into some alcohol, and the alcohol soaks up this wick, and we set this on fire, and so we end up burning the alcohol in the bottom bit here. So we have an alcohol spirit burner releasing 1,250 joules of energy into a beaker of water. The water temperature increased by 18 degrees Celsius. So again, we can highlight some of the information we need. So we've got alcohol burner released this much energy into some water, and the water temperature increased by 18 degrees Celsius. And so at least we've highlighted all the information that we have in that first bit. We need to look at the actual question though, which is how much water was in the beaker. So we need to identify first of all which quantity we're after. So I'll just quickly write I'll do it at the top here again. So Q equals M times C times delta T, and Q equals N times delta H. If you're ever wondering which equation you need to use, pretty much just have a look at which quantity you're trying to find out and which values you're given. So in this particular case, I think it's fairly clear. If we're looking for how much water was in the beaker, we're probably going to be looking at our mass. We're working with temperature changes as well, which means it's another vote for our value here. We have no information about delta H, so it's all bits of evidence to suggest that we're looking at that first equation. Now, not only are we looking at that first equation, but we specifically want to figure out what M is, like how much water. So we can talk about the mass of water as well as the volume of water. Remember, they are equivalent. So regardless, we're going to try and find M. So the first thing you need to do is rearrange this equation. So M equals Q divided by C times delta T. And hopefully we have each of these quantities. So let's just chuck some information down. So we have our Q. Actually, you know what? I'm going to be more specific. I do want you to try and do this yourself if you can. So the mass of H2O is the Q of H2O divided by the C of H2O times the delta T of H2O. Whether it's H2O or water, same thing. So the Q, the amount of energy released by the spirit burner into a beaker of water. So technically it's the Q of the alcohol, which is equal to, actually let's do this. I'm going to introduce a bit of maths here. If you've seen this before, great. If you haven't, this is what it is. So if you put the two vertical bars on each side of our value, it's showing that it's talking about the magnitude of a value. It's sort of ignoring any signs. So in this particular case, our Q of our alcohol, the amount of energy that's released by the alcohol, so the actual quantity, not the sign, is equivalent to that of the H2O, the water. So right now I don't really care about the signs. All I care about is how much. The alcohol, the spirit burner releases 1,250. So we know that the value itself is 1,250, and it's going into the water. Now, if it's going into the water, that means our Q value for our water is going to be positive. So in this case, Q for our water is 1,250, and it's a positive value because that water is absorbing it. So the Q of the alcohol, by the way, would be negative. It'd be negative 1,250. But because we're not measuring the temperature of this spirit burner and the energy is not going into the actual spirit burner itself, we care about the water because that's the stuff that we're measuring the temperature of. Okay, so we have Q. We know what C is. We looked that up. Actually, we didn't look that up, but I'm telling you what it is if you look it up. It's 4.184 joules per gram per degree Celsius again. And our delta T, I made it simple for you. I just told you how much it increased by, so it is 18 degrees Celsius. Now, if we're talking about a different substance, or we're talking about, let's say, water in a freezer, you're sucking heat energy out of the water, the temperature change will be negative, and that will affect the signs of things. So just be aware that our temperature change is clearly positive here, it's increasing. So if we put these values in, we have 1250 joules divided by 4.184 joules per gram per degree Celsius times by 18 degrees Celsius. Now again, just to make sure that we've used the right units everywhere, we have joules and divided by joules. Here we have degrees Celsius times by per degree Celsius. That leaves us with per gram on the denominator, the bottom, which will end up on the top. So again, I'll just put this onto the calculator that I have on a different screen. 1250 divided by 4.184 divided by 18 gives us this value here, 16.597. Let's go overboard. Let's chuck another 6 on the end there. And grams. So we have our numerical value. Mathematically, this value is pretty good. There's a hell of a lot more decimal points if you look at the calculator, but still, in chemistry though, and in physics, the values themselves have a meaning, and the number of significant figures that you use also has a meaning, just like we discussed in question 1. We look at all of the values that we put into this equation, and again, our change in temperature is our limiting quantity. It only has two significant figures. Remember, where we are multiplying and dividing values, quantities together. When you do that, you are just picking the smallest number of significant figures, and that's what our answer will be in. So in this particular case, the answer will be 17 grams, two significant figures. It probably doesn't feel right that you're taking 16.597 grams and turning it straight into 17, but that just shows you the importance of measurement precision. So we should be trying to measure our temperature more precisely, so using decimal points. But if you don't, and you're not careful, then obviously your values, your final numbers, are going to be less reliable. Okay, so that is how much water is in the beaker. That is equivalent to 17 milliliters, which is a very small amount. So if I was going to write this question again, I would have adjusted it so that there's more water, but not a big deal. Okay, so now for the behemoth of a question. This one took a very long time, took a lot of different steps. Honestly, this question here is probably as hard as you're ever going to see, which means if you can work with this, you're doing very, very well. Normally a question like this, all of the individual things that you need to do to find the final answer will be broken up into sort of part A, part B, part C, or A, I, etc. So I didn't do that for this one. So it was certainly a challenge. Even for those of you, those that were in the class today, probably will, some of them probably have a look at this just to make sure they understand. So, getting straight into it, we are told we have another spirit burner, but now we're told which substance it is. So that might be a little bit of a hint about something for later, but we are told exactly what substance it is and the molecular formula of it. It was this spirit burner was ignited under a beaker of 200 milliliters of water. So again, we're probably going to have to work with the mass of water. The temperature increased from 18 degrees Celsius until boiling, and the mass of the spirit burner decreased by 2.54. Lastly, I'm going to highlight this as well, and that is our final answer. We're trying to find delta H in a particular unit. So whether you can see it or not yet, there is a lot of stuff we have to do. I will throw the equations up here again. Now, if we're working with amounts of water, temperature changes, we will have to use the first equation, but then we're also working with delta H, so we're probably going to have to use the second equation again. Now, when it comes to Q, we are talking about water. So it is the Q of water. So when we're doing this equation, it is going to be the mass of, oops, a little bit nicer, the mass of water times the heat capacity of water times the delta T, the change in temperature of water. Now the reason why I'm being very pedantic about this is because a common mistake that students make is if they're told an amount of a substance that has been burnt or combusted, in this particular case we have the mass of the spirit burner decreased by a certain value, that very often confuses students and they end up putting that value as the mass. But that is not the mass of the water that's doing the absorbing of energy. That's just the mass of our substance that's been burnt. So we are looking, so I will skip a little bit of it just to make it not take quite as long, but the mass of water is our 200 grams. That's the amount of water that's doing the absorbing, so that's the number we're using. The heat capacity of water is the same as usual, joules per gram per degree Celsius again, and this time our delta T is a little bit trickier. I have added a few layers of complexity here. We'll put it up here actually while I'm doing it, just because it is a bit harder, only a tiny bit harder. We know the initial temperature. We know the initial temperature, we're not explicitly told what the final temperature is, but it does say the water started boiling. Now, quite a few people do know the temperature of water boiling, but not everyone. So just as a reminder, as long as you're at sea level, so you're not on top of a mountain, water will boil at, for all intents and purposes, 100 degrees Celsius. So I will actually rewrite this because I don't like how cramped that number is, but so it'll be 100 degrees Celsius minus 18 degrees Celsius, which will give us 82 degrees Celsius as our change. Now, just so you know, if you go to higher altitudes and you try and boil water, it will boil at a lower temperature. So, at some height above sea level, it could boil at 80 degrees. But if you aren't given any details like that, you can very safely assume that we're talking about 100 degrees Celsius. I think a student actually looked it up, and the number was actually 99.98 degrees, which is very much close enough to 100. Okay, so we've got our value here. I could talk about some significant figure stuff already, but I'm not going to because there's already enough stuff we have to do. So if we just plug this 82 degrees Celsius as our change in temperature, again, I'll do some calculations off the screen. So 200 times 4.184 times 82, that gives us 68,617.6 joules. Now, if the question was asking for this value, as in for Q, I would change the number of significant figures to give our final answer. But I mentioned in class today that I was fairly sure that you shouldn't be rounding numbers if you're going to be using them again later. And actually, while I'm here, I might as well use the opportunity to find out for sure. So on my other screen again, I'm just going to super quickly find out the answer. I probably should have done it before, but I didn't, so sue me. We have, so what sort of thing should I ask? I'll say, should we use rounded values in subsequent formula? Okay, so there is an AI bit on top. I know you can't see it, so you can just go with me. There we go. So, no, that's not what I want. I'm finding people talking about Excel functions and things like that. Riveting stuff, I know. There we go. So I've got, I found a LibreText chemistry site, and it's talking about significant figures and calculations. And here we go. Bear with me. Sorry. You can skip this bit if you want. I could probably pause it. And I don't even think this has what I want in it. It's unfortunate. Actually, that's fine. Okay, here we go. So I found, it says, so if we are doing subsequent calculations, it says when successive rounding can compound inaccuracies, intermediate rounding needs to be handled correctly. When working on paper, always round an intermediate result so as to retain at least one more digit that can be justified and carry this number into the next step. Okay, cool. So in that case, you need to have at least one more digit so that you're not, compounding inaccuracies a bit too heavily. So in that case, I believe, I know I spent a lot of time doing that, sorry about that, but we can leave at least one extra figure. So we only need 2, we can at least leave 3. I am going to leave all of them because I can. That's at least one extra. So we'll go with that. So that's our value there that we're going to stick with for calculation purposes. And we have not obviously found delta H yet. So if the Q of water is that value, what we need to realize is the change in enthalpy that we're trying to find here, the question itself, there is a slight mistake in. I remember in the classroom I actually fixed it, but I didn't do it here. So I'm going to do it now again. Again, sorry for the disruptions, but when it says what is the change in enthalpy, delta H, what that means is the enthalpy of combustion of ethanol. So delta H is telling us when a chemical reaction occurs, what is the change in internal energy of the molecules themselves. Now, when you're heating up water, you're not breaking bonds, rearranging bonds in the water. The water is just absorbing the energy that has been released from the breaking of bonds and forming new molecules in the combustion reaction. So in this particular case, when we're talking about delta H, it should be not about the water, it should be about the other reaction that has occurred to release that energy. In this particular case, we're talking about burning ethanol. So we've burned ethanol, and so we want to find the delta H of that burning ethanol. So in this case, we are looking for Q. Oops, sorry, I'll fix that. I still want it in red. So we're looking for the Q of ethanol combustion. So ethanol combustion, I know it's hard to read, but you can hear my voice. And that is going to be equal to the number of moles of ethanol burned times by the delta H of combustion of ethanol. Now, we are looking for delta H, so we need to rearrange this value, this to be, here we go, so delta H of combustion is equal to our Q of ethanol. I'll just simplify it to that, divided by the number of moles of our ethanol. So we need to have these two values, the Q and the N. Now we have worked out the Q of water. Now what you need to assume is that the Q of our water is equal to the negative of the Q of our ethanol. So when I say Q of ethanol, again, I'm not saying Q of the actual ethanol substance. The ethanol bottle hasn't released heat, but the energy that is released from the burning of it is our value here. So that means our Q of ethanol is going to be equal to negative 68,617.6 joules. So I've taken my value from water and I've changed the sign, is pretty much all we're doing here. And that is very important. Now we have one more, so we've got our Q of ethanol. Now we need to find our N of ethanol, and we do it this way. So N of ethanol is going to be equal to the equation that we've seen before from chapter 1.3 and 2.3, and that is the mass of ethanol divided by, oh, that's not going to be helpful because that looks like methanol. The mass of ethanol, I'll just make it a little bit smaller, divided by the molar mass of ethanol. And we know the mass of ethanol that's been burnt. That is 2.45 grams. We know we can work out the molar mass of ethanol. So to work out the molar mass, as a reminder, what you need to do is you take the formula for ethanol, and that in this case it's C2H5OH from the top of the question, just up here. And you need to take the appropriate quantities of each of the elements in it and add up all the appropriate quantities of each of the elements' molar mass. So if you look at the periodic table, the molar mass of carbon is 12.01. and we have two of them, so it'll be 2 times 12.01. You know what I'll do is I'm actually going to give myself a touch more space in this section here. Bear with me for a moment. I'll give myself a little bit more space so I can actually do the calculation with you instead of just talking about it. While I'm here, I might as well, as I'm recording this. So I will do the calculation for the molar mass of ethanol just down here, and then we can add it up to this spot just here. Okay, so it will be 2 times 12.01. Now again, I'm not being super explicit. I could have written out it first 2 times the molar mass, capital M of carbon, plus 6 times the molar mass of hydrogen, because we have 5 C2H5OH, so we've got 6 H's in total, and then 1 of the oxygens. But I'm going to just make it a bit, skip a small step. We add to that the 6 times the molar mass of hydrogen, which is 1.008, plus 1 times 16.00. And that gives us a number that's close enough to 46, just for the purposes of doing everything properly. So let's go 24.02 plus 6 times 1.008 plus 16. And that is 46.07. So I'll go with 2 decimal places because that is the smallest number of decimal places in any of these values, and because we're adding them, that's what you go with. So 46.07 is good enough for here. So that's in grams per mole, just so you remember. And that gives us our 46.07 grams per mole here, which will cancel out the grams, leaving us with per mole on the bottom. And well, on the denominator, which will give us moles as our final answer. So we have 2.45 divided by 46.07 is equal to 0.05. Actually, before I continue, before I write all the numbers down, I'm going to check and see how many significant figures I need. We have 4 for our molar mass. We have 2.45 for our mass. So I'm going to go with 3 significant figures. So 0.0532 moles. It was 5317, but I rounded up that 1 to a 2. Okay, so now we have Q of ethanol. So I'll highlight it just to make it a bit clearer. We have our Q of ethanol, which is for here. We have our number of moles of ethanol burned, which is here. And we're going to put those in and then do the final calculation for this particular question. So very important. Our Q of ethanol is negative 68617.6 joules. Our number of moles of ethanol, to the correct number of significant figures, I might add, is 0.0532 moles. Now, yes, this value up here has too many significant figures for what we know, or what we trust, but because I'm dividing it by a value whose significant figures are correct, so this one down here, the 3 significant figures there are legitimate, that is the thing that's going to be limiting us. So the fact that I've gone overboard with the top one shouldn't have too much of an impact. So if we go do our calculation, we get negative 68617.6 divided by 0.0532. We end up with, again, I want 3 significant figures at the end, so I'm going to go, I'm actually going to do the whole thing just for fun. So 1289804 joules per mole. And if we change this first of all to the correct number of, actually, you know what, I'll change it first to kilojoules per mole. So I'll divide by 1000, so that will give us 128.9804 kilojoules per mole, and then I'll just put a little barrier in here. To get our final three significant figures, we'll have 129. Actually, wait, what have I done? I've done something wrong. No, I put the decimal point in the wrong spot. My bad. Let's fix that up. The reason I know this is because I know this value should have been in the thousands. So there we go, 1289.804, which will be 1290 kilojoules per mole. Sorry, negative. That is a very easy mistake to make. It is a common one. Try not to mess it up. You won't lose every single mark in a question for it, but you will lose some. And so that is our final value for our delta H of combustion of ethanol that we've calculated in this experiment. Now, what the next part, the final part of this question is asking us to do is to actually compare it with the accepted value of ethanol for the combustion of ethanol. So, so I'm just going to quickly Google the combustion enthalpy of ethanol, and we have found is equal to negative 1366.8 kilojoules per mole. So that's the accepted value. So when people do the experiment really well, they make no mistakes, their design is quite good. Again, the equipment will be quite advanced. That's the number they get. And we are comparing it with negative 1290 kilojoules per mole. Now, these numbers are different enough that it isn't just the number of significant figures that has had the impact. If the numbers were pretty close, then that might be an impact. But because they're significantly different, we need to have a think about what has caused this difference. Essentially, what we're saying here is that we have calculated that the ethanol isn't releasing as much energy as we expect, or as it should. When you do burn ethanol, it is going to release the correct amount of energy. It is going to release the 1366.8. Again, assuming that some things such as complete combustion and things like that, but again, probably a bit too much detail. In our experiment, we have put a little ball of little glass bowl of ethanol with a wick in it. We've ignited it, and we are expecting the heat to go into a beaker. As I'm sure you understand, if you were to put your hand somewhere near the flame, to the sides of it, or even near the sides of the beaker, you will feel some heat from the flame that does not go directly into the beaker. Instead, it's being lost directly to the atmosphere. So that is going to be, when we do the experiment, that is going to be the major source of our difference. Now, this value here of 1290 is actually fairly close to the value, all things considered. The value that we'll probably find in our experiment is going to be closer to negative 400 sort of area, which means there's a lot of loss. But just to summarize, heat from combustion is lost to let's not say atmosphere, let's say environment. Environment means everything around it. The heat from combustion is lost to the environment, the heat from the combustion is lost to the environment, which accounts for the energy that didn't into the beaker of water. So when you do the experiment, a lot of the heat will not go into the actual water. It's the same thing as on a gas stove at home. you will get a lot of heat going around the container, around the bowl, and that heat is lost. And by lost, I just mean it's not doing something useful, our use for it. If I'm trying to heat up a saucepan, that heat is not going into the saucepan. The heat itself is just going wherever it wants. It's not really, lost to itself. It doesn't have feelings, but it is lost from our perspective when we have a particular use for it. If we are trying to put that energy into this beaker of water to be able to measure the energy released, any energy that does not make it into that beaker of water, going out to the sides, out to the environment, is lost, and it does not, contribute to our water going up, and it'll seem like the ethanol is not releasing as much energy as it actually is. I think that's pretty much it. So thanks for bearing with me, especially for that little section in the center where I tried to make sure that my handling of significant figures in subsequent calculations was all right. And hopefully, you can follow it all. And for those of you who did do it in class, hopefully this helps, and hopefully the ones who missed it, it's understandable. I'll see you next time.